hoping that I'm going to fit it within 35-40 minutes, leaving some room for discussion. Stas Glubakovsky asked me to present, and thank you very much.
But before you do that, Roman, before you do that,
yeah.
I would like to formally introduce our speaker. We start with these graceful moments. It was 12:34 on my phone, so I thought we would wait for another minute for that. But let me start with that. So today we have Dr. Roman Makhnenko, who's an assistant professor at the University of Illinois at Urbana-Champaign, and I'm sure that he will be soon converted into an associate professor. So Roman graduated, got his, can I say, master's from Moscow State University, so the same university I hold the PhD from. Then he went traveling, went to Minnesota to Emmanuel de Tournay Group, which is well known in the field of geomechanics and rock mechanics. And after that, he proceeded his traveling show and went to EPFL in Lausanne, another strong group. So he's been focused on rock mechanical measurements in the lab all this time. And then he got that position at the University of Illinois, where he now has a lab and a few brilliant students. So take it away, please, Roman. Thank you.
Thank you. Yeah, almost correct presentation. So I just wanted to say that, yes, we're rock mechanics group at the University of Illinois. And the work that I'm showing today is done in the framework of two projects. One that we are working on for the last 4 years, Carbon Safe, Illinois Corridor, and also SMART initiative for using machine learning in CO2 storage. And the title is very pretentious: Integration of lab and field scale rock mechanics measurements for geologic carbon storage. And this work is mainly done by my senior PhD student, Nikita Bondarenko. So if by any chance you think that this is something interesting and you're looking for a good postdoc, you can find his information on our website. So let me move on. CO2 storage, I hope is capture and storage. Most of the people are aware what's happening. Potentially can be a game changer in climate change mitigation, be responsible for almost a fifth of the reduction in greenhouse gas emissions. And the capture, of course, part is very important. We have a power plant here on campus, and I took this picture when it was like minus 17 Celsius. So our power plant, from all the pipes we use in natural gas and coal, it's like just shooting the smoke in the sky. And now we actually have a project where the capture is happening at this power plant, and then the liquefied CO2 is transferred through the pipelines to the storage site. And Illinois Basin is famous for some projects on CO2 storage. I'll show you in a minute. But the idea is that we can actually capture the CO2 and inject it underground. We used to use the word sequestration, meaning permanent storage, but I think storage is like more wide, because sometimes we think that we can get back there and get part of this fluid for some purposes. The idea is that for the permanent storage, that we will have the formations in a way that you inject in a porous material, but we have a cap rock that prevents leakage. We will have CO2 dissolving in the brine, and this is another trapping mechanism. The small CO2 particles will be trapped in the small pores, and also CO2 is mixing with the brine and making acidic solution and making basically a new rock. So we hope we can store it there for thousands, millions of years, basically forever from our perspective. And here in Illinois Basin, there were two projects that have been implemented, both pilot scale, meaning that potentially we want to upscale for by, at least an order of magnitude in terms of the injection. So for Illinois Basin Decatur project, it was 1 kiloton per day injection, so 1 megaton totally was injected over 3 years. That happened in 2011 till 2014. And then the next project was actually exploring the same formation. It's called Mount Simon Sandstone, but the middle layer. So there is a lower layer of Mount Simon, and we're talking about the depth of around 2 kilometers here and maybe 1900 meters in this case. There was the second project, which also now I believe is complete. It happened from 2017 till 2021. For the setting is kind of ideal for CO2 storage, and we're not, it's not like that everywhere. We know that there are countries, there are states where we have mainly crystalline and basaltic rock and not too much space for storage, but Illinois Basin is fantastic. We have this thick, 500 meters thick Mount Simon sandstone layer, which the porosity varies, but between 15 and 30%. We have the caprock, Eau Claire shale, also relatively thick. They're quite heterogeneous, but should be a good caprock. There are actually a lot of other layers here, including 2 other potential caprocks. But the most interesting part is what's happening actually in this particular project underneath the injection site. So the injection happened in the first stage at lower Mount Simon sandstone. And then there is some intermediate layer. Sometime before the project actually started, it was considered to be part of Mount Simon, but now we recognize it as a separate layer, Argenta sandstone. And you can see from the log data that the parameters are changing, maybe not abruptly, but kind of you can see the boundary between these 2 layers. The porosity of Argenta is smaller, around 8%, I believe. Permeability is also could be like 3 orders of magnitude smaller. And then right underneath it, there is this Precambrian rhyolite, more than 1 billion year old rock that actually contains a lot of fractures. It's I will be showing you some pictures, but that kind of led to observation of induced microseismicity. And of course, with my pretentious title, we could have like a short course on this topic, but I decided to focus on just a few things and mainly related to this Illinois Basin Decatur project. So induced seismicity is the concern for underground storage operations, and it's mainly, we know, coming from wastewater disposal in the US, and we see the abnormal rise in the number of observed earthquakes, and now we can recognize, I think USGS has a fantastic website where every day you can see where the events are happening, and you also can distinguish between the natural and human-induced earthquakes. So the reasons, of course, we know all over the world there were geothermal projects failing because of induced seismicity. Wastewater disposal is a big factor in conventional oil and gas exploration. And it hasn't been yet a big deal in geologic carbon storage, but of course, the point is that carbon storage hasn't been realized really at industrial scales, and we should be aware of what's happening, and that of course, we are pushing for this technology to be implemented, and we don't want large earthquakes to happen. So this motivates our research in this area, where in general, the subsurface fluid injection, how can we study it? How can we combine the laboratory observations? This is what we're mainly doing, with some data obtained from the field. And of course, Illinois Basin Decatur project is also unique because the monitoring that has been performed was outstanding, and I think it's on my next slide. No, sorry, let me get, yeah. So for this project, on the left, I'm showing the seismic events that were happening in Illinois Basin before the project has started. In fact, most of the seismic network was installed around the injection site 2 years before, and very few events were recorded. And then when the CO2 injection, 1 kiloton per day, has been performed, the events have been recorded. Of course, depending on the magnitude, we can talk about hundreds or thousands or tens of the thousands of the events. So most of them are with a very small magnitude. You can see by coloring, right? And the largest magnitude was around 1.2. But also this clustering of the event was not uniform. The distribution, spatial distribution, and in time was a little bit unexpected, when sometimes, if events were a few months after the injection were happening 1 kilometer away from the well, and then a few months later, just in another location 400 meters away from the well. And we saw different explanations, including chemical effect, that it's happening. But in general, if we get to the reasons for potential induced seismicity, of course, the most popular one that is considered is the diffusion of the pore pressure. You inject the fluid in a reservoir rock, you increasing the pore pressure locally. The state of stress is assumed in first approach to not to change. Sorry, it's going by itself. So basically what's happening is that you're increasing the pore pressure. The effective normal stresses in 2 or 3 directions, depends on what kind of model you use. They are decreasing, and at certain point in certain location, your more circle can touch locally the failure envelope, and most of the time it happens on the fault. Faults are having smaller cohesion, sometimes smaller friction than the intact rock, so you can induce an earthquake. Now, the next level of consideration involves looking at the coupled processes where the changes in pore pressure are modifying the Mohr circle by itself, because you're inducing the poroelastic stresses, right? Your rock is deforming due to the change in the fluid pressure, and that changes the state of stress surrounding it. And of course, there also could be a thermal component here, because we know that most of the time CO2 is reaching the formation at lower temperature, so there is some cooling effect. I'm not getting there. And then, of course, locally, we can also look at the shear slip. We can look at some other processes, but mainly, again, caused by the changes in fluid pressure. And another important factor is that the geometry, the stratigraphy by itself, could be quite involved, right? We need to look at the 3D faults. We also oftentimes don't know very precisely the state of stress. Even for this project where, step rate tests were performed to measure the state of stress around the injection well, so we know it more or less precisely, but this has been done only for the reservoir. And the observed seismic events, I didn't mention that yet, because it's probably on my next slide here. Yes, the observed seismic events were mainly happening underneath the storage formation in the basement. And in fact, most of those kind of what we think now faults, they were not really mapped before the injection. So if we think that this clustering of the events is corresponding to faults, some of them were not mapped. So the basement here is playing a crucial role, and we need to understand why is it happening. And of course, another interesting story is that when I started working on this project in late 2016, there were very few specimens that we could test from the basement and this intermediate formation, Argenta, and all of those specimens were actually not, it was not possible to test them in conventional triaxial tests. So they were all too small. We could only measure velocity and density and porosity of those. So then it was another well that has been drilled, Terra Macmillan, 10 miles away from IBDP wells. And purposefully, I think that the idea was that at some point it will be used for CO2 injection. So we've done some work on it. And this well allowed recovering course from this intermediate layer Argenta between the injection interval in Mount Simon and the Precambrian rhyolite, the basement rock. So we recovered some specimens, did some microimaging, did petrophysical characterization, did porosimetry, trying to explain why the seismicity could be happening there. I can tell you that it was quite challenging preparing those specimens, especially from the rhyolite, because basically very few of them didn't have the apparent fractures. And even if they didn't, when we were trying to core through them, they were falling apart. So I believe that the expenses associated with drilling this well were more than, for sure, $5-7 million. They purposefully went to the basement, and then, you know, we take these pressures, 1 billion or 1.3 billion year old rock, and every time we're trying to prepare a specimen, it starts falling apart. We can actually not do a good job. So we most of the core we destroyed, but we managed to prepare a few specimens. We managed to measure some of the properties. The material is quite stiff. You can see the Young's modulus around 70, right? And the compressional wave velocity 5.3, 5.5. The porosity is below 1%, and the pore size distribution also shows just nanoscale pores in it. This is speaking of the rhyolite. However, again, we managed to make a few intact specimens, and we did what a lot of people do, assessing the potential for induced seismicity. We measured the triaxial strength of these materials, found quite high friction angles, so 42 for Argenta, 61 for the rhyolite. For the rhyolite, we assumed that, let's say for the fractured material, the cohesion should be 0 because we have fractures, but this still wouldn't explain the seismicity. The overpressures for the pilot scale project in Illinois Basin were not exceeding 1 MPa. I think they were actually not even exceeding 100 PSI, so 0.7 MPa. And looking at this diagram here, we say that, or at least at least should be 10 megapascals to explain why the fractured basement was failing and producing some little earthquakes. So we decided to look, and again, we're using the state of stress here, just reported for the, and adopted for kind of the basement, but reported from the injection interval. So we decided to use a more comprehensive approach where we do not only the conventional triaxial compression tests on dry cores, but we look at those other mechanisms that I mentioned before, including the poromechanical coupled processes happening in those materials, as well as studying the flow properties of those fractures and the intermediate layer as well. So we developed some experimental equipment over the years, and I was just discussing with someone recently that for some of these projects, we're investing more money that we get in from them just to get the equipment going. So one of the things that we're kind of proud of, now we have 2 of these devices, is core flooding, and it's purposefully used for testing low permeability rock, where we can fully saturate it and actually use it for multi-phase flow. I don't want to go into multi-phase flow, but actually we did it for even crystalline low permeable materials. Here it's important that we're managed to fully saturate the course. We measure Skempton's B coefficient. We measure that it's not changing at high pore pressures, showing us full saturation. So we can assess the hydraulic properties of the material. These are some of the results. So we have Mount Simon sandstone from the injection interval. We have Argenta, the intermediate layer, and we have the basement. For those materials, we can measure Skempton's B coefficient. I'm showing it on the left. You can see the stress dependence of this poroelastic property, relatively strong stress dependence. And then on the right, I'm showing the permeability. So we have some estimation for the intact material because we ran some diffusion tests, so only one data point. But then the most interesting part, of course, is for the fractured basement. So we have a few specimens with a sealed fracture. And you can see here that very much depends how you set up the specimen. The permeability could vary by 5. I think that we had results when it was 7 orders of magnitude. So when you have the fracture open, of course, most of the flow happens through it, and the permeability could be up to a Darcy. And then when you have the sealed fracture, when we have this intact specimen, we manage to make those pressures cylinders, then the permeability is, on the order of below micro Darcy. This is something that we will use in the future. And then also this intermediate layer, the micro Darcy is the order of magnitude for Argenta. So comparing to Mount Simon, it's actually 3 orders of magnitude less permeable, and it partially is working as the seal for the basement fractures. And then I show that we have this triaxial, a kind of advanced triaxial cell, actually, where we can monitor everything and do 2-phase injection and microseismic activity, but we also trying to run like a few tests simultaneously, because you understand, right? When we're talking about the materials of this order of magnitude of permeability, measuring of some of the parameters on fully saturated specimens takes months. Nikita, my student who mainly contributed to this presentation, this was actually his first project, and I think that like his first year was very challenging because to get a few data points, it was taking a lot of time. So we're trying to use a few experimental devices at the same time, and we have now this hydrostatic cells also, where, let's say, if we don't really specify that it has to be axisymmetric compression, we can do just hydrostatic and measure some of the poroelastic properties. And now we can do it again when we have multiple fluids and we have elevated temperature. So and also irregular specimen shape, which is very important in case of this natural course that we get, because sometimes it's difficult to prepare a good specimen. And this material, again, is very precious. So for hydrostatic compression tests, this is how our specimens look like. And some of them we believe had fractures, some of them we called intact, even though, on some of those that we called intact and we ran triaxial tests, then they failed through the pre-existing planes. So maybe there are just some fractures that are not visible for us. And as I showed on this image here, so we did X-ray CT, and you see we didn't really see that there was a fracture for this one, but you can see it from the CT scan. Or I think here we're kind of already taking this part away. But again, there could be fractures that we don't see in them. So intact is just a name for the apparent appearance of the material. So these hydrostatic tests allow us to measure the drained and solid or unjacketed bulk moduli, and these are the important parameters in our model because they are responsible for the poroelastic coupling. You probably remember 1 minus k over ks prime is Butte coefficient. So stress dependent drained modulus, quite stiff basement rock, order of 30, 40 gigapascals. And then the solid parameters also kind of for Argenta and Mount Simon, typical for the sandstones, and then the basement is more stiff. There's some feldspar and other elements, so the values are higher. And now, of course, this could be again another presentation on the poroelastic relationship, but we make it quite simple, is that we can use now these parameters to take into account the hydromechanical coupling, where it's not only the effective stress that is changing due to the hydraulic effect and injection increase in the pore pressure, but there's also the deformation of the rock that is happening. So the mechanical effect, because the pore pressure has this coupled effect on the rock behavior. So, and now we get into, okay, where can we use this data, right? So of course, I'm not really making emphasis on the velocities. That was our very first project, to give those seismologists the velocities of the formations, preferably at representative in situ conditions. But now, moving further, for what can we do with this data that we have obtained? Let's say we have a full set of poroelastic properties, including shear modulus, undrained, drained, and unjacketed parameters. Can we now model what happens during the injection? Can we represent the faults, and can we predict some of these seismic events? And the first approach that we used was almost like a 2D, but we used 5 planes, and then in each plane we were just looking at the 2D effect, where we had a few faults there, and one of the faults was just under the Argenta, so we wanted to see what this intermediate layer does to the potential effective state of stress, and hence seismicity, as well as some faults that were directly connected to the reservoir. So they were conduits for sure for the fluid flow. So this is how the modeling is done, finite element, right? We just solving these equations in the grids of our numerical domain. And this, first, of course, we had to create a model where we take the conditions that were reported for this site in terms of the vertical and horizontal stresses and pore pressures, and these are the static conditions before the injection happens. So there is, of course, already, if we prescribe that they're false, there are places for the stress concentration there. But of course, the most interesting things are happening when you start the injection, and that would be when the fluid pressure starts increasing, and we see that indeed it appears that if the faults are directly connected to the injection interval, this is maroon Mount Simon sandstone, then the pressure increase, the pressure buildup on those faults, they are larger than on the one that is separated. I hear some noises. Is this a question, or should I just continue? I would assume I continue. So the pressure increase is smaller on the fault that is separated from the injection interval by the Argenta layer. But poroelastic stresses in general making faults more prone to reactivation. And this is a 2D model. Doesn't really predict much. Again, the change in pore pressure, 1 MPa, not enough to observe seismicity. So we are moving forward and now trying to work with the 3D domain. So looking at 3 layers, lower Mount Simon is shown in blue, Argento, green, and then basement. And the size is, we're looking at the area around the injection well, which is shown in red, and those black are the observed seismic events. And here, that's the point where we realize that our kind of standard approaches and simulations also using CPU, they would be very time consuming, even if we have, the domain with maybe tens of thousands, maybe hundreds of thousands grid points. It takes weeks, sometimes months to see something. So that's where we kind of maybe switched our attention from geomechanics and went a little bit to CPU versus GPU modeling. So it appears that if you go for GPU, then and you have multiple units, it really accelerates these because the computations are done in parallel and they're optimized. So it really accelerates the process. And here's the comparison for using GPU versus CPU. When we get to the millions of grid points, and this is the case, of course, for us, where we have the injection site, and we know that the events were observed around a mile away from the injection site, and then we also need to have some resolution, of course, vertically. So need to have a good 3D grid network. So we need millions of grid points, and then GPU gives huge advantage. Let's say the factor of 30 or 40. So instead of spending 6-7 months, we could spend 4 or 5 days to get the reliable data. Now, of course, the question is in terms of the accuracy, and that's the simulation that Nikita did that shows that the pressure, the accuracy and pressure is for CPU versus GPU is negligible. It's 10 to minus 16. So we can assume that it's working quite well, and that means that we can move to large scale simulations, and that's what we're currently trying to do. But again, the big question is how well do we know the state of stress at the places, at the faults where the events are happening. So here on the left figure, I'm showing kind of where the state of stress is supposed to be, and then I'm showing the failure envelope. So we're kind of not there yet. But again, there could be other things. There are some involved fracture networks that could bring us even closer to the failure. And also the plot on the right shows that the basement could be, based on our calculations, the one that is most critically stressed and the one that is closest to failure in this case. So that's where we're at right now, is that on the left here are the mapped faults, and then in red color is the events that were observed during Illinois Basin Indicator project. There are 2 wells, CCS1 and CCS2. Most of the events were produced by CCS1. And on the right, we're again showing the events in red, and the coloring scheme shows the proximity to failure based on our model. And the darker is the color, the closer we're to failure. And we think that in first approximation, we have some agreement in terms of that the model independently kind of showing these darker zones around the places where events were happening. So there is still, of course, there's still some modifications that we can do, but we believe that this approach is slightly more comprehensive, but hopefully more reliable than just the standard more column on dry rock. And now I wanted to, so this was kind of some of the lab testing and modeling, but of course, this question of upscaling and using the lab data in general for interpretation of the field measurements and some predictions for the projects in general, this is a comprehensive question. When I was interviewed for faculty positions, I think at every department they were asking it, and every time I wanted to ask them back, do they know how to do upscaling? I think a lot of people don't. But in any case, the approaches that we're trying to develop are going through multiple scales where we can get some useful information even from microimaging, and we use some methods where we can get contact angles and some even friction properties at the very small scales, micrometer, millimeter. We can combine it with the lab data. We also have, especially for these two big projects in Illinois Basin, high quality well log data as well as the seismic data, and then need to come up with just proper models that can allow us to represent what is happening, and usually that involves quite complicated geometry. Now, our other project also deals with use of machine learning in carbon storage. So I wanted to show some preliminary results here where we used, again, Illinois Basin Indicator project is so well monitored and so much data is collected that even people who worked on it sometimes are not aware how much we have. So one of the things that we looked at was that we have this high quality FMI log where we actually can see the fractures from the borehole data, so we know where they are. And at the same time, we can look and see how the parameters that we get from the log data, for example, mineralogical composition, resistivity, density, and velocities are correlated to each other, meaning that can just from this standard 1D geophysical log data, we predict where the fractures are located. And of course, it's important. These are the fractures that are just crossing the well, but in general, it is important to know where the fractures are. As I mentioned at the beginning, most of these, what now we think are faults in the Illinois Basin, they were not mapped before the injection started. So, so we looked at this the correlation of the log data, and the training data sets were those where we had FMI log and high resolution fracture images. So basically, we told the code where the fractures are, and then it can see how it correlates with the parameters. So we managed to do some mapping of those fractures in terms of the angles, orientations, and the depth. And we used 6 different machine learning algorithms. So XGBoost, light logistic regression, and others, and try to see if they can predict. So now we have a few boreholes. We can use those best boreholes with the best data for the training, and then we use others for testing. And the general conclusion, so I'm kind of showing in low resolution all 6 results, but basically it didn't work for us. So we couldn't see a good accuracy in predicting the fractures. And again, this is of course an involved topic because we're looking, the data is recorded every half a feet, so every 15 centimeters, and the very few places where the fractures are. So most of the time, of course, there are no fractures, and the prediction is that there are no fractures. But in those places where the fractures are, none of those codes can accurately predict their presence. So, and we saw that actually, when we use if we train the data on the same information, that would be the best way to do it. So it's not even the same location and well, but it should be the same information. If you use the information from there, then you have some predictive power. Otherwise, I think that it's not really working well. So this is one of the ways to look at it. And another thing that we're currently exploring is actually combining the log data and the lab data that was collected for Illinois Basin Indicator project and other projects in Illinois Basin, and also trying to use machine learning approaches to see if we don't have enough lab data. I was surprised because, I would say half of the data that we need comes from us, from my group. Not very good kind of correlation and not very good understanding why it's needed, or because another big thing that I probably didn't spend enough time explaining is that we need better accuracy in determining where those seismic events are happening. We still have this seismic data is still kind of low resolution, because if the seismic velocities are changing with depth, they can change. Of course, they change with the formation, but with depth and pressures and temperatures, they also change a lot. And it was not considered in interpretation of this data. So we can have errors, 5-10%, maybe more. And this is a big deal, because the events could be probably coming not from the basement, but formations on top of it. But yeah, we need better accuracy, and that means that we need better data. And now we're looking at how this high resolution log data, for example, mineral composition, can we predict some of the parameters based on that? Can we again train our models on those places where we have the exact results, where we did the direct measurements? Can we train our models and then use this training data to prepare codes, to prepare neural networks that will be able to predict more precisely the properties of the formations in the places where those properties were not measured, of course, were not recovered. So this is part of the ongoing work, but basically these are kind of our preliminary efforts in combining lab characterization, field observations, and modeling. And this was motivated by these projects in Illinois Basin. We think that this combined approach is comprehensive. Of course, they require scientists from different areas. I believe that we're one of the best groups in terms of lab testing, but modeling and machine learning and other aspects, including field observations, we're happy to discuss and happy to collaborate. So this is kind of a new topic to me. I just wanted to start some discussion and give you some food for thought, something to think about over the break. And some of this information is contained in these papers. So it's mainly me and Nikita who are working on it over the last 3-4 years. Thank you for the attention. Stas, we cannot hear you. At least I cannot hear you. Damn it. Stas, I don't know. Can anyone?
Roman, this is Tom Daly. Can you hear me?
Yes. Hi, Tom.
Okay. Well, we're waiting for Stas. I'm not sure what happened, but so I'll say thank you. That's a very nice talk. And I like the integrated approach you're taking. I think that's very worthwhile to pursue. As you said, it's difficult when you have your own area of expertise to try and bring in the other things, but I think it's ultimately the right thing to do, as will probably hopefully be done on large projects. Hello, Stas, is that you? Still don't hear you.
And
okay, I'll just continue.
Keep going, Tom. Yes.
Yeah. I had a couple of questions. One, so the core issues. I mean, it's really I feel sorry for your problems trying to get samples from the core, as you said. You spend a lot of money drilling in to the basement. And for how far into the basement did they drill?
So I believe it's around 60 feet, just around 20 meters. So I think. Can you hear me? Yeah,
I can. Yes.
Yeah. So it's around 20 meters. I might be mixing up some wells, but I think that's what at least we have here. And of course, yeah, this is a very good question, because if we go deeper, how different it is. But it's all it's all expensive drilling through those formations.
So presumably the top of the basement is the most fractured and most less intact, right?
Yes, that's what they believe. And then I'm not coming from geological background, but I was trying to get those cores right when I started here, and they were saying we don't have them, but Precambrian rhyolite is exposed next to Mississippi River on Illinois-Missouri boundary. Let's take some of this weathered material from there and test it. And I said, no, it doesn't work like this.
No, I know. That's a geologist talking. So I assume, it's obviously a problem when you try and remove these cores and you unload them, and then you take them into your lab and they fall apart. So I'm glad you got some intact samples. Clearly there's a lot of uncertainty there about the actual rock properties. Right? Yeah. So are you confident that your intact samples really are intact?
Yeah, it's a good question. I think that yes. So for those three, I think that we had a failure that would be corresponding to the apparent fracture angle. We still saving a couple more. We want to do them with seismic monitoring, so we will be enhancing this data. But I can tell you that our ratio of success versus not success was like 1 to 3. So we failed a lot. And if you look at this understanding, as you mentioned, right, how precious they are, we decided not to. We still save them for maybe more comprehensive tests with fluid pressure and temperature. So, but those that were showing, we had maybe 5 tests. 2 of them failed through some planes that were there, and 3 of them failed through we think it was the intact material failure. Yeah. So
yeah, that's too bad. One other quick question. I may have missed this. How did you map the faults in the basement? How did they come up with those locations?
Or Stas supposed to know it better. Can we make it interactive and you respond to this question?
Yeah, I know.
Out from the audience. So can you hear my voice now? Does it work?
Yes.
Okay, sorry, I don't know what happened. So, Tom, basically, they traced the faults that also intersected the reservoir. So they only saw those faults in the seismic, that caused some sort of offset, at least at the Cap Rock reservoir boundaries and the reservoir basement boundaries. So, but these faults are known to disagree with the clusters of the microseismic events.
Yeah, because I saw the seismic data back 10 or 15 years ago when it was first being acquired, and it looked to me like it'd be very difficult to interpret anything in the basement. I was wondering if it had been improved in quality. Otherwise, it would be not very trustworthy.
Yeah.
If I can jump in.
Yes, Jim.
I left a chat comment around slide 23. My question was basically, when I listened to you talking about lab testing, maybe I wasn't listening carefully enough, but I didn't really understand which pore fluid you were using, say, in your compressibility tests or some other testing, because you and I both know liquid CO2 has a very low viscosity.
That is true. And
brines. And it seems to me, if you want to think about where liquid CO2 is going to go in the subsurface, the answer is it's going to go wherever it wants. and it's going to have a very low viscosity and flow easily through some of these fractured rock media. So I was following your discussion of these compression tests, and I wasn't really clear what you're doing in terms of your pore fluid here.
Right. So for the for the poromechanical parameters, the bulk moduli dry modulus is measured for the dry rock, and the solid modulus, the injected, is measured for oil saturated, because that's oil is our confining fluid that we allow to penetrate inside the pores of this material. For the permeability measurements, we don't prepare this same brine as we have in situ. We just use, distilled water. We wanted to exclude some chemical effects. So these measurements in the core flooding device are done with water. I'm not showing, we did some tests with CO2. I'm not showing the result because we looked at also two-phase flow. I would we didn't like first we excluding some of the things here, of course, and one of the important things is temperature. I don't think that temperature will be very important for the mechanical properties of this rhyolite. I think from my experience, it should not change much. But of course, in terms of the viscosity of the pore fluid, right, and CO2 being in the supercritical state, I agree with you that it can travel everywhere. This could be the crucial factor. However, we're looking at pressure currently, right? The effect of the pressure. Obviously, when you have two phases, the pressure inside the fluid is not uniform, and there will be some redistribution. But we believe CO2 doesn't go to the basement. The mapping of the plume shows, some redistribution in the host rock around the injection interval, but we think that what goes to the basement is still the brine. It's just the changes in the brine pressure that are causing changes on the effective stress state and allow us to observe some seismicity. So we're not yet,
I was asking you to go back one slide. You're looking at bulk modulus data on the right-hand screen.
Here, yes.
This one, intact basement. Do you have a feeling for what the mineralogy is that's giving you a bulk modulus of 65 GPa?
Yes, thank you. It's a good question. I'm getting back to my I think we have mineralogy. So quartz, feldspar, some calcite, some dolomite. I think it is very close to be the upper boundary for this material because, some of these minerals have around 70 GPa bulk moduli, when some like quartz have around 37, right?
Right.
But I'm not showing the plot again, but I think that we're like very close to the potential upper boundary of what the mineral modulus can take for this material. However, there are almost no pores, so it's possible, and I tend to believe my data because we use the same device and same approach for different materials, where let's say for those which are quartz aerenites, we get very good agreement with the bulk modulus of quartz itself.
Thank you very much.
Thank you, Jim. Those are very good questions. I appreciate it.
Yes, absolutely. So we have one more question. Harry, would you like to unmute yourself?
Sure. Yeah, thanks for a really interesting talk. I just wanted to follow up on Jim's questions about the fluid properties. Do you think that having different fluid properties, different viscosity, compressibility, might change the poroelastic coefficients in the material, which fundamentally have to do with coupling the solid with the pore fluid, and also maybe their stress dependence? And to sort of expand from that, do you think that might have implications for seismic dispersion and the velocity models you're talking about in event locations?
So maybe I start from the end, right? Yeah. For the velocities, for sure. We know that velocities are, or especially compressional, dependent on the type of the pore fluid, mainly the compressibility of the pore fluid. When we have CO2 plume or we have more dense brine, they will be affected. Now, for the poroelastic, right? So elastic kind of to me means that, okay, Skempton's B coefficient. Of course, when we have CO2, there's a separate studies. You see, Stas told me 40 minutes talk, 20 minutes for discussion, and I still want to bring my daughters to their last swim practice of the year today. So I thought I should not go there when we have two fluids. I agree with you that this is a very important question. Now, some of the parameters, Skempton's B coefficient, for sure, we have a little bit of CO2, the pore fluid becomes much more compressible. We measure smaller P wave velocity. Skempton's B coefficient is going down. For the solid and bulk moduli, theoretically, they should not change, right? However, and I didn't mention it here, of course, there are a lot of things. Temperature, right? I didn't talk about caprock and some clay inclusions, but chemistry. So my first PhD student, his PhD was on the chemical effect. And we see that if you have a little bit of calcite, you can have dissolution, even a little bit. Even in the caprock, you can have some dissolution, change in properties, increase in permeability that would affect everything. Clays are also becoming reactive with brine CO2 mixture. But also we start seeing that, let's say, those things that we sometimes neglect in those poroelastic models, because we look at everything kind of from static standpoint, but let's say viscous behavior, time-dependent deformation, creep, they become much more pronounced. And that also influences the velocities. My work mainly in this area was in shales and clays over the last few years. And then we see some significant changes. I think that for the basement, maybe it's not that important, but for Argenta, it does contain some clay. For the Mount Simon, yes. So velocities for sure will change. In terms of the model, Skempton's B will change. But again, the question is that, and this is next level that we need to go to, is the multi-phase fluid flow, which is very difficult to predict because the material is heterogeneous. And I didn't really talk about it, but we see, we looked at the caprock and we recovered those cores, same borehole, just a few meters difference. It could be very different clay and sand content. So in one place we say, oh, it's an ideal caprock. The breakthrough pressure is high. There will be no fluid flow, no CO2 flow. In other place, more quartz and you have some conduits in the caprock. So heterogeneity, of course, is another thing to how to model it at different scales. That's another question. But yeah, thank you. I think that it's a very legible question.
Roman, can you make a quick comment on reactive transport in the presence, not of carbonate, but you have feldspars? Is that maybe not too important, or do you think you might have that in the future?
Yeah, my experience is not that big in this area. I tested Berea sandstone that had some feldspar around 7%, as well as we tested this Precambrian rhyolite, and then we had also charcoal granite with some feldspar. Basically, when we flush CO2 away and measure the properties after CO2 flow, we see them being the same as before. So but our lab scale testing is few weeks of CO2 treatment. During this time scale, we don't see it. I think that if I talk to some people from Earth Science department, they would tell me you need to go to 300 degrees Celsius and 3 years of treatment, and then you will be able to see something. Let's write a proposal about it. But at the lab scale, at the time scales that we use, we don't see the effect for the feldspar, as well as quartz, actually. Thank you.
Any more questions? So we scheduled our talk until 1:30, and I believe that Roman needs to go and take care of his daughter. I mean, I have a couple of questions, but I will ask them offline, I guess. So, and we should thank you for the wonderful talk. So
thank you.
You can hear at least my applause. So and the guys online, I just wanted to say that this was our last talk for the year, and we will see each other in 2024. So a lot more exciting things are coming our way. Thank you.
Okay. Thank you very much for having me. Happy holidays.
Thank you. And bye, everyone.
Thank you. Thank you, Stas.